In today's lesson from section 2.1, we'll be taking a look at graphs of functions and also the graphs of their derivatives. So if you have the graph of a function, you can approximate the graph of its derivative function by estimating the slopes of the tangent lines at various points. If the slope of a tangent line is positive, then you have a positive y value on the derivative function. If the slope of the tangent line is negative, then you have a negative y value on the derivative. So when you're graphing the derivative function, you're graphing the y values that you get by looking at the slopes of the tangent lines. So in our first example, we have the graph of a parabola, and we're going to draw a series of tangent lines and just estimate their slopes. So if I start on the left-hand side of the parabola, notice that the function is increasing. So if I draw a tangent line at this point over here, the tangent line would have a positive slope, and notice that the line is pretty steep, so we're going to approximate that slope as positive 3. So if you just go directly above that point, all the way up to positive 3, put a point right above that. So that blue dot represents the slope of the tangent line drawn down here in the graph. So take a look at another point in the graph and we'll estimate the slope. So if I draw a tangent line at this point, notice that its slope is also positive, but it's not quite as steep as our first line. So while the slope is still positive, it's a little bit less than what it was in our first point. So it might be there at positive 2. And again, we're just approximating what the slope is. If we take a look at the vertex of our graph, if I draw a tangent line at that point, notice that it's a horizontal line, so its slope would be 0. So if I plot that y value directly below that point of tangency, we have a point right on the x-axis. Now notice on the right-hand side of our function, it's decreasing, so the slope is negative. So if I look at this point, it has a negative slope. And so we'll come down and approximate that around here, around negative 2, not quite negative 2. If we come down further on our graph and we draw another tangent line here, it's going to have a negative slope, but it's even smaller than the slope of our previous tangent line, so it might be down here. Now, if you take and you connect all of those points, you see that our derivative function, this would be f prime of x, that I've graphed in blue, f prime of x. Our derivative function is a line. Okay, so keep that in mind. Its degree is 1 degree less than this degree, than the parabola. Next, we're going to take a look at the worksheet problems. So there's a copy of the worksheet available in the classroom, but I've also placed it on our Google Classroom page, so you can download it and print it out at home. So some helpful hints. If the function is increasing, the tangent line has a positive slope. The steeper the curve, the larger the slope. And vice versa for decreasing functions, a negative slope. Soft turns or curves happen when the derivative is 0. In other words, we have an x-intercept at that point. Sharp turns happen when the derivative is undefined or you have a vertical asymptote or break. And we'll use that a little bit more later on when we're trying to graph a function given some information about it. All right, but for now, we're going to do a little bit of matching. So on the left-hand side, we have a graph of a function, and on the right-hand side, we have all the graphs of the derivatives. Okay, and number 1, notice that it's a linear equation, and its slope is negative. And what we know about the slope of a line is that it's constant. So this slope is going to be negative throughout the line. So its derivative would just be a horizontal line. So number 1 is a match with C. Again, because the slope is negative, and we have this line drawn that it's down below the x-axis, so it's definitely a negative value for the slope. and the slope of a line is constant, so that's why the slope stays the same over every value of x. Okay, number 2, we have a parabola, so check it out. We can use the graph to get a picture of the derivative before we try to match it. So on the left-hand side of the graph, we have tangent lines that would have negative slopes, and this would be negative. It's going to go to 0 at the vertex, and then the function starts increasing, so the slopes are positive. Okay, so we're looking for a graph that's going to show us negative slopes going to 0, becoming positive. Right, if it helps you to try to graph it, so if it had a negative slope on this left-hand side, and it would be a rather steep line with a negative slope, so I would put a point down below here. This next tangent line isn't quite as steep, so it's coming up. Here the slope is 0, because it's a horizontal tangent line. Now the slope is increasing, it's positive, the function's increasing, the slope is positive, so it's coming up, and it's becoming even steeper. So this right here is the graph of the derivative function, all of those points. So number 2 is a match with D. To take a look at D right here, shows that the slope is negative, goes to 0, and then is positive over there. Okay, so negative slope, 0, and became positive. Okay, so the derivative of a parabola, you're going to find it's always going to be a linear equation. So number 3, we have a cubic function. So if we start off by looking at the slope of the tangent lines, here it's positive, right? So it could be up here. Here it's positive, but it's not quite as steep, so it's coming down. Here it becomes 0. And then on the right-hand side of this function, it starts increasing, so that would be a positive slope, so it's coming up. And then it would be a positive slope here, even steeper. And if you check it out, the graph of the derivative function is a parabola, and that's going to be a match with F. Okay, because you notice in this graph of the derivative, here the slope is positive, it's 0 at that point, and we have positive values for slopes. Okay, so the function is increasing, decreasing, but the derivative is positive or negative, because the derivative is the graph of all the slopes of your initial function. All right, for number 4, if we take a look at this function, notice that it's decreasing, so there's a negative slope. So it could be about right here. There's another negative slope. It's kind of flattening out, so the slope is approaching 0. Here it's negative. Here we're approaching 0. So the graph of the derivative would look like that. So number 4 is a match with B. Okay, so it's showing that the slope is always negative, right? Because the function is always decreasing. Okay, so 2 more in here. Moved it up a little too high. Okay, so in number 5, we've got a 3rd degree polynomial. So notice that's increasing, so positive slope. Positive slope. It's going to go to 0 here, and then goes negative, and then goes to 0 again, because it turns at that point, and then the slope is positive, positive. Okay, so we're looking for a function where the slope is positive or 0 everywhere. So if you check out those points, we're looking for a parabola, and this time it's a match with the graph in A. Okay, because there was a little section in there, sorry, where it did become a negative slope in here, where it made that downward shift. So that shows that it goes below the x-axis, so slope is negative for just a little bit of that graph. All right, in number 6, we have a function that is always decreasing. Okay, so the slope is always going to be negative. So if you take a look at it here, this tangent line has a negative slope, a negative slope, negative slope. Over here, that tangent line has a negative slope, negative slope, negative slope. So because our function is always decreasing, the derivative function will show only negative values in it. So that's a match with E. Okay, so it takes a little bit of practice. I also posted a link to the Khan Academy video where you can actually watch the video and then you have a chance to practice it yourself. And I think it'll help you understand the graphs of the derivatives even better. Okay, next we're going to try to take some information about a function and its derivative and draw a graph based off of that information. Okay, so in the first problem that we're given, we're going to draw this just on a simple xy axis. Okay, the first thing that we're told is that f of 0 equals negative 5. So that tells us we have the point 0, negative 5 as one definite point on our function. Okay, so we're graphing the function, not the derivative. All right, we're going to use information about the derivative to get the rest of the function. It says f prime of x is greater than 0. In other words, the derivative is greater than 0 if x is greater than 0. So on the right-hand side of our graph, it's going to be increasing because it says the derivative is positive, meaning we have a positive slope. So what that means for our function is that it's increasing. So if you start at your point 0, negative 5, and we show an increasing function, notice that we have half of a parabola. Now remember, we're just sketching, so we're not going to be any more precise than having that point at 0, negative 5 and showing that it's a parabola. The third line says that f prime of x is less than 0. In other words, it's negative if x is less than 0. Okay, so that would mean that our slope of our actual function would show us being negative, but the function itself is decreasing. So that's going to finish off our parabola like this. Okay, so again, if you draw in the tangent lines, you'll notice that the slopes are negative for all those tangent lines. They go to 0 and then they become positive. Okay, so we're not worried about graphing the derivative at this point, we're just graphing the original function. This last piece, f prime of 0 being equal to 0, tells us that our function is defined everywhere. So this means that we have a soft curve. So it comes in, goes to that vertex, and then curves around and starts increasing. Okay, for the next function, let's start off with the xy axis again. Remember, we're graphing the function and not its derivative. So in this case, we have g of 0 equals 0, so it's going to go through the point 0, 0. And it says the derivative g prime of x is greater than 0, meaning it has a positive slope. For x is greater than negative 2 to x equals positive 2. So we're going to hold off on graphing that just yet, but something's happening between negative 2 and positive 2. It's increasing, okay? Okay, the derivative g prime of x is less than 0, meaning we have a negative slope for a function for x less than negative 2 or x greater than positive 2. Okay, and now it tells us that g prime of x is undefined at positive 2 and negative 2. So that means that we're going to have sharp turns. At negative 2 and positive 2, okay? So there's something happening at our function at negative 2 and positive 2. Now keep in mind that between negative 2 and positive 2, our function has to be increasing. So I'm going to draw in a line going this way, okay? So that's x equals negative 2, x equals positive 2. It doesn't matter what the y values are, okay? You're just showing that this function has a positive slope for every value between negative 2 and positive 2. Okay, when x is less than negative 2, it has to be decreasing, or the function has to have a negative slope. So it could go something like that. And then when x is greater than 2, it's also decreasing. So it could go like that. Again, this is just a sketch, but make sure that you show that whatever your graph is, that it matches all of those intervals. Okay, our third example probably has the most specific information. We're given three functional values. It says f of negative 3 equals negative 2, so graph that point. So left 3 and then down 2. Okay, then f of 5 is equal to 0. So that's an x-intercept. And then f of 1 equals 4. Okay, so you see how that kind of breaks up the graph into different sections. We have to figure out what's going on in each section. Before I start to graph the function, I want to figure out if there are soft curves or sharp turns. So this last line is the most important. It says f of x is differentiable everywhere. So that means for us that we're going to have soft curves. Okay, so no sharp v's like we had on the last one. Okay, so the derivative, f prime of x is less than 0, so it has a negative slope. In other words, our function is decreasing. When x is less than negative 3, or between positive 1 and positive 5. Okay, so between x equals 1 and x equals 5, it has to be decreasing. Okay, well, I'm going to go back just a little bit there, because we're going to have a curve at that point. And also, when x is less than negative 3, it's decreasing. So it could be coming in this way. Okay, so you see if you drew tangent lines to each of those two pieces, the slopes of those tangent lines would be negative. Okay, the second line here says f prime of x, meaning our derivative, our slope is positive if x is between negative 3 and positive 1. So here we're going to be increasing. So those tangent lines would have positive slopes. And also when x is greater than 5, we should be increasing. So it should be a soft curve over here. So we want to come in, soft curve, go up like that. And that's it. Again, these are just estimates of what our function would look like. The functional values should be graphed accurately, but we don't have any other points, like specific points to graph. Okay, finally, number 4. We're just going to do this really quick. It says the derivative is negative for all values of x. So there are a couple different, or many different options. Okay, so we have a negative slope. You could simply draw a line that has a negative slope. Okay, and if it has a negative slope, this one would be constant, like the derivative function would give you a graph that looked like that. You could draw some type of curve like this. That's always decreasing. Excuse me. So the slope of the tangent lines would always be negative. Or you could even draw a graph, again with a curve that maybe looks like this. because it's always decreasing. Therefore, the derivative or the slope of any tangent line would be negative.